We have talked about the expected value of perfect information. But what if perfect information is not available? In fact, in reality, we rarely have access to perfect information. However, we might be able to utilize additional information, such as the result of the survey, to improve our estimation for some uncertain outcomes and improve the decision. Therefore, the next concept we are going to discuss today is the value of imperfect information. We use expected value of sample information, sometimes called expected value of imperfect information, to capture the maximum worth of the imperfect information in a decision problem that involves uncertainties. So how are we going to do it? Similar to the steps for calculating the expected value of perfect information, we will need to find the difference between the best expected payoff with sample information and the best expected payoff without sample information. Let's use the following example to illustrate the concept. We are evaluating how much the market research firm's information worth. In order to do that, we will need to compare the expected monetary value of the best strategy if we choose to do a local survey versus the expected monetary value of the best strategy without doing the local survey. We first utilize the decision trees to visualize the decision problem. First, we want to find out the expected monetary payoff for the best strategy when we do not have a local survey. There are two options: to launch the product or do nothing. If we launch the product, then there is a 60% chance that it will be a national success and a 40% chance that it will be the national failure. Therefore, the expected payoff for launching the product is 3 million times 0.6 minus 1 million times 0.4, which is equal to $1.4 million. The expected payoff for doing nothing is $0, of course. Therefore, the best strategy is to launch the product, and the expected payoff is $1.4 million. The next step is to find out the expected monetary payoff for the best strategy when we do a local survey. If we do a local survey, then there are two possible outcomes for this local test. The local test could be a success or a failure. As a decision maker, regardless of whether the local test is a success or a failure, you still need to decide whether you want to launch the product. If your decision is to launch the product, then the product may turn out to be a national success or a national failure, and the payoff will depend on the national market. When we take a look at this decision tree, we will realize that we need the probability that the local test will be a success or a failure. We also need the conditional probabilities that whether the product will be a national success or a national failure, given the local test result. After we fill in these probabilities, we will be able to calculate the expected payoff when we do a local test and choose the best option accordingly. Now, let's look at the probability information we have. We have the prior probability. We also have the conditional probabilities for the market research firm's track record based on the historical data. However, we do not know all the probabilities that are relevant to this decision. The probability of the outcomes from the local test and the conditional probabilities for the national success or failure given the local test result. Fortunately, we will be able to utilize law of total probability and Bayesian theorem to find out these probabilities. First, let's calculate the probability that the local product test succeeds. The probability of local success equal to the probability that local test is a success and the national market is a success, plus the probability that local test is a success and the national market is a failure. Then, by multiplication rule, we can obtain the probability using the prior probability and the conditional probabilities that are provided in the problem description. Next, we can utilize the rule of complement to find the probabilities that the local test fails. Then, we want to find the conditional probability of a national success or failure given the local test is a success. To get that, we are going to utilize Bayesian theorem. We first write down the probability based on the definition. The top part of the equation is obtained by multiplication rule. The bottom part of the equation was obtained by law of total probability. After some calculations, we can find that the probability that the product is going to be a national success given that the local test is a success. By rule of complement, we know that the probability that the product is going to be a national failure given that the local test is a success is 1 minus 0.871, which is 0.129. Similarly, we can use Bayesian theorem to calculate the probability that the product is going to be a national success given that the local test is a failure. Again, we start with the definition. The top portion is obtained by multiplication rule. The bottom part was already calculated earlier. Therefore, the probability that the product is going to be a national success given that the local test is a failure is 0.1579. By rule of complement, we can find the probability for the remaining branch, which is 1 minus 0.1579, which is 0.8421. Now, we are ready to calculate the expected payoff when you do the local test. Remember that we calculate the expected value backwards. We first look at the subtree in which the local test is a success. The expected payoff of launching the product given that the local test is success is 3 million times 0.871 minus 1 million times 0.129, which is equal to $2.484 million. Compared to do nothing, launching a product has a higher expected payoff. Therefore, you will choose to launch the product given a successful local test. Next, let's look at the subtree in which the local test is a failure. The expected payoff of launching a product given that the local test is a failure is 3 million times 0.1579 minus 1 million times 8421, which is equal to minus $0.3684 million. Compared to do nothing, launching the product has a worse expected payoff. Therefore, we will choose not to launch the product given a failed local test. Now, we can clearly see from the tree that the best strategy given the local test outcome and the corresponding expected payoffs. That is, if the local test is a success, then launch. If the local test is a failure, then don't launch. Therefore, if we do a local test, then the expected payoff will be 2.484 times 0.62 plus 0 times 0.38. And it is equal to $1.54008 million. Then, the expected value of sample information is 1.54008 minus 1.4. which is 0.14008. This is the maximum amount of money we will be willing to pay for this sample information. Let's recall the steps. First, we find out the expected monetary value of the best decision when we do not have sample information. Next, we assume that we will get the sample information for free and find out the expected payoff when we act optimally accordingly. Then, you find the difference between the expected monetary value with sample information and the expected monetary value of the best decision without sample information. And that gives you the expected value of sample information.